Assalamualaikum warahmatullahi wabarakatuh. Hi 11 graders, how are you today? Hope this video finds you well because now we are going to talk about webs. I'm sure that you already know that webs are almost everywhere. For example, when I'm talking to you right now, my voice is transferred by webs. And you can see me through your screen, it's also transferred by webs. It seems that webs is helping us to communicate with each other, right? And interestingly, not only that, webs also help us to navigate a certain area. Another example, when you don't have any idea how to reach a certain area, so you can just take your mobile phone and open a map and choose a location as your destination. Then the maps will show you which road that you will take. And yeah, as simple as that, yeah, everyone. So basically, your mobile phone is emitting and receiving webs to get the data. It seems interesting to discuss about webs, right? So for now, we are going to talk about some quantities of webs. They are displacement, amplitude, wavelength, period, frequency, and speed. If you are interested in this topic, please keep watching and let's start by saying basmalah. Bismillahirrahmanirrahim.
Okay, everyone. So today we are going to discuss some quantities of webs. But before we start discussing okay, everyone. So today we are going to discuss some quantities of webs. But before that, here I would like to show you an example of webs. Yeah, this is transverse wave. Okay, let's see this simulation, everyone. Okay, maybe to make us easier to analyze, I will make it slowing down. Okay, like this. Yeah, as you see here in this simulation, we have orange dashed line. Yeah, it shows us that this is the equilibrium position. Yeah, this is the equilibrium position because before this string oscillate, yeah, the position all the particle here is in this dashed line, so we call it as equilibrium position. Yeah, okay, and then here now the string is oscillating. You see, yeah, that actually webs only travel the energy, not the particle. You see these green balls only move upward and downward. Yeah, it's not moving to the right. What is moving to the right is only the web itself, yeah, which is transferring the energy. Okay, the first quantities that you have to understand here is the displacement. Okay, to understand about that, I will pause these waves. Okay, right now. Now, you see, displacement is actually the distance from a point of the web to its equilibrium position. Yeah. Okay, let's say I pick this green ball. Yeah, this green ball or this green particle. Yeah. We have a distance, yeah, from this green ball to its equilibrium position. So this is the displacement of this point. And then this red ball also has distance, yeah, between it and its equilibrium position. So it has displacement. Yeah. In this simulation, we can use a ruler to measure the displacement, everyone. Yeah, we can use this vertical ruler. Therefore, the green ball, yeah. Okay, you see, the displacement is around, okay, until this one, and then divided for how many division? 1, 2, 3, 4, 5, and the 5 divisions. So for each division has 0.2 centimeter. Yeah. So the displacement of this green ball is about 0.8 centimeter. Yeah, that's the displacement. And also another example, what is the displacement of this green ball? Yeah, you can just use this ruler, okay, and then you can just read the result. Here it's around 5 centimeter, no, not 5, yeah, 0.5 centimeter. Yeah, 0.5 centimeter. Yeah, so that's displacement, the distance of a point on the wave to its equilibrium position. Okay, the next one is amplitude. Okay, this one is more simple and it's easier to understand because the definition of amplitude is just the maximum displacement. Maximum displacement. So from these waves, we can identify the maximum displacement is here, right? The maximum displacement. So we can just measure again. Yeah. Nah. Yeah. So this is the maximum displacement. It's around 0.8 centimeter. That's the amplitude. Yeah. One more time. Amplitude is maximum displacement. Okay, now we already have two quantities, right? Okay, the next one is wavelength. Wavelength. Yeah, we can describe wavelength as the distance between two adjacent points on the wave that's oscillating in step with each other. Yeah. So from this simulation, one wavelength is a distance from this point until this point, yeah, from this peak to next peak, yeah. And then we can use this horizontal ruler to measure the wavelength. Okay, now you see, so the wavelength of this wave is around 4.1, yeah, 4.1 centimeter. That's the wavelength. Okay, one more time. Wavelength is distance between two adjacent points, yeah, that's oscillating in step with each other. Okay, that's wavelength. Okay. And then the next one is period. Yeah, period. Okay, to discuss about period, maybe here I need to use timer. Okay, and I will dismiss the ruler first. Okay, okay, this is the timer. Okay, a period is the time taken for one complete oscillation. Yeah, one complete oscillation, that means one wavelength. One wavelength. Okay, I will start this simulation again until, okay, yep, it's hard yet to, yeah, okay, yeah. So this green ball, it starts from its equilibrium, yeah. So from this simulation, one wavelength should be from one peak to another peak, or this green ball should be moved upward, backward, and upward again until it's reached the original position. Yeah. Okay, let's see. I will start and stop when this green ball already make one oscillation. Okay, yeah. Start. Stop. Okay, yeah, it's around 0.65. Okay, maybe if it's too fast for us to identify. Oh, it's actually we already used the slow motion mode here, yeah. Okay, let's try again to find the period. Remember, period is the time taken for one complete oscillation. Yeah, so we can just observe one particle here when it's moving upward, downward, and upward again until it's reached this equilibrium position. Yeah. Start. Stop. Okay, yeah. So the value is around 0.6 and 6 seconds. That's the period, the time taken for one complete oscillation. Okay, and then the next one is frequency. For frequency, we can just describe frequency is the number of oscillation in a unit of time. Yeah, mostly we use or we calculate or we measure the frequency for 1 second. Now, so for that, I will start this, what is it? This stopwatch, and then I will count how many oscillation that already have by this simulation. Okay, only 1 second. Yeah, it's really fast. Okay. Okay, I think it's hard. Okay, I think that's all for now. We will continue later.
Okay, student, now we are going to discuss about period. Period can be described as the time taken for one complete oscillation. Okay, to identify one complete oscillation, you can pay your attention to this first green ball when it's already reached its maximum position and move downward and back to the maximum position again. So we already get one oscillation. Yeah, and then we can use this stopwatch to measure the time. Okay, get ready. When the green ball reach the maximum position, we can start the stopwatch, and when it's already back to the maximum position again, so we can stop the stopwatch and we will get the period. Okay, get ready, start, stop. Okay, let's try again. I think my reaction time is too long. Start, stop. Okay, yeah. So this is, we get 0.65 seconds. And then we can conclude that the period of this wave is 0.65. Okay, 5, not 7, sorry. So the period of this wave is 0.65 seconds. Okay, one more time. Period is the time taken for one complete oscillation. Okay, the next quantity is frequency. Frequency can be described as the number of oscillation per unit time. Yeah, one more time. Frequency is the number of oscillation per unit time. So if we already know the period, we can just simply use an equation to get the frequency. Yeah, we can use the equation F frequency equals to 1 per T, 1 per period. So when we already know the period is 0.65, so the frequency is 1 per 0.65. Okay, you can also calculate by yourself, everyone. Okay, and then this is what I get. What I get is 1.54 hertz. Yeah, remember the unit for frequency is hertz. Okay, this is what I get, 1.54 hertz. And then compared to the set of the simulation here, the frequency is set by 1.5 hertz. So yeah, close to the setting. Yeah, of course, when I measure, there is uncertainty. Yeah, based on my reaction time, based on another factor. Yeah. Okay, so one more time, frequency is the number of oscillation per unit of time. Okay, and then the last one, speed. Now, to find the speed of this wave, yeah, it's quietly simply, yeah, we can just use an equation for uniform motion. Yeah, that's mean a motion that travel with constant speed. Remember, to find the velocity, we can just use the equation V equals to S per T, displacement or distance per time taken. Yeah, same to this condition. So for that, to find the speed, we have to count, sorry, not count. We have to measure the time and also the distance. Yeah, so that's why here we need a ruler, yeah, to measure the distance. Okay, I will show the ruler again.
And at this time, we use the horizontal ruler. Okay, how to measure the distance? Yeah, here I will set a reference of 5 centimeter. Yeah, from this point until this point. And then when this green ball reach its maximum position, and then it will generate the peak of the web, and the peak will move to the right. Yeah, you see. Now, when this green ball reaches the maximum position, I will start the stopwatch. And then when the peak moves to the right and reach 5 centimeter, I will stop the stopwatch. Yeah, so the time that's shown by the stopwatch is actually the time for the wave to travel by 5 centimeter, and then we can calculate the speed. Okay, let's try. Okay, first we need to restart the stopwatch, of course. Yep, and get ready. Start. Stop. Okay, yeah. Here the time that I get is 0.81 second, and the distance is 5 centimeter. So you can use your calculator to calculate the speed. Yeah, the speed is distance per time taken. So 5 centimeter divided by 0.81. Okay, this is what I get. 6.2 centimeter per second. Yeah, 6.2 centimeter per second. Yeah, so to find the speed of this wave, it's simply you can just divide the distance by the time. Okay, one more time. So the speed of the wave is actually the distance traveled by a point of the wave in a certain time. Okay, that's all the quantities for today, everyone.
Okay, student, that's all from me. Before we end this video, let's summarize what we have learned today. Now, you already know that waves at least had 6 quantities, right? First, displacement is the distance from its equilibrium position to a point on the wave. And then the second is amplitude, is the maximum displacement. And then the third is wavelength, is the distance between two adjacent points on the wave that oscillating in step with each other. And the fourth is period, is the time taken for one complete oscillation. And the fifth is frequency, is the number of oscillation in a certain time. And the last one is speed, is the distance traveled by a point on the web in a given interval of time. Okay, that's all the 6 quantities of wave. Thank you very much, everyone, for your watching. But if you still have any question or need further explanation, please do not hesitate to contact me. Yeah, I will help you, of course. Okay, that's all from me. Once more again, thank you very much. Let's close this video by saying hamdalah all together. Alhamdulillahirabbil alamin. I close this session. Assalamualaikum warahmatullahi wabarakatuh. Bye bye.